Okay, what I would like to do now is to talk about uh, so my plan for today is I will talk about NP completeness um, and do one of the things that I always find fun, which is and hopefully it'll work this year, is the NP completeness challenge. But we'll talk about that a little bit later. Um, what I wanted to start off with is the what you call it. I guess I wanted to start off with the problem of the day. Um, it looks like I don't have my slides actually for the Bandersnatch Bobilly thing. You've probably heard me talk about this many times. Let's just go ahead about it. What was the Bandersnatch Bobilly thing? If I have an algorithm, Bandersnatch of G, that works by converting G to something called Y, calling Bobilly of Y. If I have an algorithm to solve the Bandersnatch problem, which works by translating the input, which is a decision problem, whatever decision problem you want. If I have an algorithm that works by translating the input to Bandersnatch, G, into a different format called Y, such that the Bobilly problem on Y is always equal to the answer of that's always equal to the Bandersnatch problem on G. If I have an algorithm like this, it could mean two different things. It means one of two different things. If I have a fast Bobilly solver, this would give me a fast Bandersnatch problem solver, assuming the translation is linear or something like that, linear, quadratic, cubic, something like that. Okay? You give me a polynomial time, running time Bobilly solver, this would give a polynomial time Bandersnatch solver. But if you have a guarantee that the Bandersnatch problem is so hard, there is no fast algorithm for it. This algorithm is what proves that Bobilly is hard. If Bandersnatch is a hard problem, and you would have a fast Bandersnatch solver if you solved Bobilly quickly, then this means Bobilly is hard. And that is the reasoning that we use about NP completeness. Any questions about that reasoning before I go any further? Okay, the logic of this needs to be kind of clear. Any comments? Okay, so the problem of the day here is show that hitting set, okay, is the hitting set problem is NP complete. What is a hitting set problem? In the hitting set problem, you've got a collection of subsets. You have some subset S, okay? And you've got a collection of subsets of S. C1, C2, C3. Okay? And you've got a bound K to make it a decision problem. And we're asking, does the set of elements, do there exist K of these items such that every subset that we're input has at least one representative from our subset? Okay? If you want to think what hitting set problem is, the hitting set problem is about finding representatives. Let's say I had wanted at the beginning of the semester to form a student committee to come to talk to me about issues in 373. There are people in this class, P1 to probably about P, 160 or so. Okay. And if I wanted a representative committee so that all your grievances would be heard, you guys probably fall into certain constituencies, right? Some of you maybe are seniors, and some of you are men, and some of you are women. And some of you may be members of the Crips, and some of you may be members of the Bloods, okay? You could imagine a world where you guys are all representative of certain groups. My subsets here are what are my different groups. And if you guys are going to come to me as a committee, okay, I would want somebody, okay, who is, I would want a small committee with the property that every group has a representative. Does that kind of make sense that that's a property you would like to have? I could make sure everybody is represented, but then I've got to see 160 people. Forget it. Time of COVID, forget it, especially, right? But maybe a small group would be good. And so I want a group of people, a small group of people, such that each one of my constituencies' input are covered. Okay? I have at least one representative there, right? Now, it would be great to have a student in my class who was a sophomore, who was a woman, who was a Crip, okay, who had all kinds of different properties, okay, because they would tick off a lot of constituencies. But the hitting set problem says, find me the smallest, namely a set of size K, of people such that all constituencies are solved. Any questions about what the problem is? Do people understand the problem and why this is a real-life problem? Okay, if we deal with this, if we want to prove that this problem is hard, is hitting set Bandersnatch or Bobilly? This is how I like to think of it. If we want to prove hitting set is hard, what is it going to be?
Bobilly.
Bobilly, right? So here I'm going to be calling hitting set. And it looks like my input to hitting set is I've got a universal set S. I've got a collection of subsets C and a bound K, right? What should my Bandersnatch be? Does anybody have a feeling about what Bandersnatch is a good Bandersnatch for here?
Vertex cover.
Vertex cover. Why do you think vertex cover is a good Bandersnatch? Hello? Anybody want to tell me why? What? How? It should be true if the problems smell the same. Do the problems smell the same?
Vertex cover deals with like having subsets.
So vertex cover is about finding subsets of things which are representative things. In this case, the things that you want to pick are vertices. You want to pick a subset of vertices in vertex cover, right? So what was vertex cover? Vertex cover said I had a graph of vertices and edges, and I had a bound J, right? And the reason you like this one, I think, is because of what? Because you're telling me kind of that in vertex cover, you want to pick a small set of vertices such that what? Is it every edge is represented? That's kind of what it is, right? Okay. So tell me now, what is the mapping? How do I convert my vertices, my edges, and my J into an S, C, and K such that I could use a hitting set solver to solve vertex cover? Any proposals?
I propose that for the set S, we take the set of vertices.
You want to claim the set of the universal set is a set of trouble. Let's see if I can do that. J. You want to claim that S is going to be the set of vertices, V1 dot 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 Vn, right? What else do you want to claim?
The collection, each subset in the collection is an edge. So you have like edge with ij, you'd put I and j in the subset.
1, E2 dot 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 EM. Okay, and each edge EI is going to equal to sort of, X and Y, X comma Y. It's a pair of vertices, right? And what is K?
J.
So if we are doing this translation, you're telling me, okay, that instead of class members, I am going to have the set of vertices. The committees that I'm going to have, the possible constituencies, are going to be the edges. So each one of these constituencies, these subsets, is going to be only 2 people, right? Two vertices. And we're asking, is there a set of J vertices such that every edge has at least 1 vertex? That is, in fact, exactly what vertex cover is. And that is what hitting set is. Does everybody kind of see that?
Professor, could you clarify what C is again?
C is the collection. So in hitting set, C is, if we're going to make the analogy to the class, S is the students, C is the groups, okay, and K is my bound. In hitting set, I want to know, find me a set of K students from S, such that every one of the groups that you guys think you have formed, okay, has at least 1 representative, okay? And likewise, what this construction is telling me is pick a set of at most J, vertex cover is telling me, pick a set of at most J vertices, such that every edge is one of the members of that set. And that every edge has at least one of its 2 vertices in what I picked. So it's sort of saying, give me a congress of J vertices such that every edge has a representative in Congress. That's kind of what it's saying, right? And looked at this way, the 2 problems are in fact the same. Does everybody agree with that? This is a nice reduction, a nice simple reduction, okay? And and again, this is the kind of thing that is, a great ideal thing. Hitting set seemed like an interesting problem, but we know that this problem is as hard as vertex cover, which is as hard as anything else, okay? So it's as hard as SAT, okay? And SAT we know is hard. Any questions about this? Okay. Any questions? Yeah, again, people seem to dislike my programming style. That's what I keep reading about on the chat room. You're saying, why do I create these variables? Well, I think I do it for clarity, right? I got to fill in all the slots in the arguments. This is how I like to do it. Okay. Any questions? Any questions about this reduction? This is the level of reduction that I would be, is perfectly fair for me to ask you on an exam. Any question? Going once, going twice. Okay, sold. Again, I worked out an example here got a little confused last year, but with a problem called set cover, if you're interested in seeing a real worked out example of the idea, this would work. But I think people kind of get it now. Any questions? Okay, what I would like to talk about now is, again, some of the art of how you prove problems NP complete. Okay, and again, you're trying to show that two problems are the same. That is kind of the heart of what you call it. That's the heart of the matter here. And there's a question just about the exam that the proof is to show a reduction like that. You should show a reduction like I've been showing. But of course, it's good to have words to explain why it is. If you're writing down random things, okay, it's going to be wrong if we don't understand what exactly you're writing. You want to kind of make the analogy between the two problems, showing what is the same, what has the right role. Okay, so the pseudocode is the heart of the NP completeness proof. But I encourage you on the exam to explain ideas you have, just to make sure we don't miss it. Any questions? Okay, so the heart of proving something NP complete is to basically show that two problems that superficially look different really are the same, okay? And they're not necessarily the same, but at least a special case of each other. So there's two different kinds of, sort of ideas that people approaches that someone will prove that something's hard, okay? So one is to show that the problem you care about is a special case of, has as a special case an NP complete problem. Let's say that I want to tell you the problem, you wanted to argue with me that the problem of finding the longest path in a graph. You have a graph, you want to find a path where it visits the most possible vertices. Okay. If I say, given an integer k, can you show me that there are two vertices such that there is a path involving that many edges between them? Okay. This problem, if we let the length of the path be the total number of vertices in the graph, n minus 1, and then subtract 1 from it, that would be asking for a path that visits all the vertices in the graph. That problem is called Hamiltonian Path. That's a hard problem. Okay? If Hamiltonian Path is hard, okay, that means finding a path of length n minus 1. Then if I ask you, because it visits all the vertices, if I ask you, is there a path of length k, is that hard? Well, it's certainly going to be hard when you ask k equals n minus 1. Any questions about it? So if your problem is a more general version of an NP complete problem, your problem has to be as hard as the NP complete problem. That's what we mean by restriction. The other idea, or another idea that you guys would be thinking about, is kind of, sometimes you want to show that your problems really are the same, not that one is strictly harder or more general than the other. And by making changes to things, little changes to your problem, maybe you can argue that that the problem is the same. So one example of this, again, when we did 3-SAT, okay, we proved 3-SAT was hard by taking a SAT problem and doing little local changes to everything. Another example, which maybe is harder to explain than it needs to be, the graph isomorphism problem is about showing that two graphs are the same. So there's a graph. Here are two graphs on 4 vertices. Are those two graphs the same thing?
Yes.
Okay. Suppose I give you this thing's adjacency numbers. This was vertex 1, 2, 3, 4. This is sort of, let's call it 1, 2, 3, 4. The problem of isomorphism is showing that two graphs are the same up to renaming the vertices. Okay? If you want to show that it's just as hard to do it for bipartite graphs as any other graph, what if I do a little transformation where I add another vertex to split each edge? It should be clear that if you know how to find the isomorphism between this graph and this graph after they're divided, you knew how to do it before they were divided. It didn't really make the problem any easier or any harder. But now these graphs are bipartite, so you've got red and green vertices. So that's an example of a local change and shows that whether the graph is bipartite doesn't make it any easier to solve isomorphism. Any question?
So in that example, the isomorphism would be the Bandersnatch, and the isomorphism on bipartite graphs is a known hard Bobilly.
So again, which should be harder, isomorphism on bipartite graphs or isomorphism on general graphs? Which should be harder?
The general case sounds harder.
Right. So if I had an isomorphism solver for a graph, actually I could solve, it's pretty clear I could solve bipartite isomorphism on G if I had an isomorphism solver. If I had a fast general isomorphism solver, I'd have no trouble with bipartite graphs, right?
Right.
But now, if on the other hand, what I really showed was the alternate one, which I showed that if I wanted to solve isomorphism, okay, and all I had was a bipartite isomorphism solver, I showed how to convert G to some graph G prime that was bipartite. And if you could solve it, if you knew how to solve bipartite graph isomorphism quickly, you would have solved the other one. So this is the argument that bipartite isomorphism solving is as hard as general solving. Any questions?
So someone did a similar thing for bipartite isomorphism then to prove that is NP hard, so we can now use that.
Okay, well, let's say I'm not quite saying that, okay? It turns out that isomorphism happens to be a problem one of the very, very rare problems people don't know if it's hard or not. But I can tell you that if you were to, that it's no easier, this argues that it's no easier if it's bipartite, right?
Right.
Okay. So if someone came to my door and said, oh, I want to solve graph isomorphism, and I'll say, I don't know how to do it. If they then were to say, well, what if my graphs are bipartite? I'd have to still say, I don't know how to do it, right? This is what the argument is.
Gotcha.
Okay, any questions? Bang. Okay, so how do you go about proving that problems are hard? Again, when you look at these reductions, once you understand it, it's, I find proving problems hard a pleasant and straightforward thing to do. And the right way to think about these things is to realize that if you want to, like a piece of code. If I gave you to, if I ask you to write a program for doing something, it's usually easier for you to write the code from scratch than to take some diseased code from someone else in the class and try to understand it. Okay? An NP completeness proof is sort of like writing a program, right? So, you know, I find that often they are easier to create from scratch than to try to explain one. Okay? And let me give you sort of the ideas that you go about doing to try to prove that. If I want to prove that a problem is hard, you have a problem, your boss gives you, you want to prove that it's hard. How should you do it? Okay. So my first claim is you're doing any NP completeness reduction was a Bandersnatch being converted to a Bobilli. And this was to prove that Bobilli was hard, right? If you want to do this, what should you use as your Bobilli, as your Bandersnatch, your known hard problem? My recommendation is that you make your Bandersnatch as simple as it can be while still being a hard problem. Why is it that we like 3-set better than set? Both of them are equally hard. Why do we like 3-set generally better? Okay. It's more restrictive. If you're doing a translation, you've got to translate every possible instance of your Bandersnatch into a Bobilli. Now, the more restricted what you are translating is, the easier it is to do the translation. Knowing everything clause was of size 3, okay, makes it easier than if it's arbitrary length clauses, right? So this is the first thing. So when I am proving things NP complete in the real world, I will never use traveling salesman problem as my Bandersnatch. Why? Because I would like something restricted. The traveling salesman, where the graph has the triangle inequality, meaning the weights are such that the distance from X to Y is always less than the distance from X to Z plus X to Z to Y. That problem is hard. But even more restricted is the Hamiltonian cycle problem. Given a graph, find a way to walk over all the vertices such that you visit every vertex once before getting home. That's a simpler version of TSP. Okay? Hamiltonian path, where you have to visit all the vertices but not get home. That's even simpler. You know, the simplest version of Hamiltonian path that I know is hard is that if the graph is a directed planar graph where every vertex has at most degree 3, meaning one way in and 2 ways out. Okay? This problem is still hard. So when I'm doing my translation, in general, I'm willing to use as simple a version as I can. Any question, simplest hard problem that I can. Any questions about why that's my strategy? The other thing is I want to make my Bobilli problem as hard as possible. Remember, I'm trying to convince my Bandersnatch into Bobilli. I want every possible Bandersnatch instance converted to Bobilli. If I want to prove Bobilli is hard, I should try to make the hardest version of Bobilli. What's harder than than the Bobilli problem? What about weighted Bobilli, where the thingamabobs have weights? Does everybody agree that's more general than an unweighted version of Bobilli? What about directed weighted Bobilli, where every thingamabob has a weight and there's also a direction on the thingamabobs? Does everybody agree that that's a more general thing? The more general it is, the harder the problem presumably gets, because the hardness of the problem depends kind of on the worst case. So if I get stuck, I will try to make my problem that I'm trying to prove hard even harder. And then when I understand how to do that, maybe I can get rid of these extra things that I added. Any questions about that? That should be clear is a good strategy. The key to making reductions easy is in general to select the right source problem, okay? The right Bandersnatch, okay? And the way I usually do it, I have only kind of 4 problem types that I use as my Bandersnatches in general. I use 3 sets when nothing else seems to work. I use integer partition, kind of, can I find or find a subset of numbers that adds up to a target, these kind of problems, when I'm working with number problems. I use vertex cover for any problem on graphs where the hardness is depending upon selection. Select a set of vertices, select a set of edges, but typically select a set of vertices, okay? That smells like vertex cover. And Hamiltonian path is kind of the canonical problem that is for graphs where you're trying to do an ordering on the vertices. Any questions about that?
Just a quick question about like semantics and like wording. I know you said generally you want to make a problem more general for Bandersnatch. But you said like
No,
to
I
do
want my
make it more
Bandersnatch to be simple, restricted, but still hard. And I want my Bobilli to be as general as possible to make it easy to do the reduction. That's what I'm saying.
okay.
Does that make sense?
Yeah.
Okay, any other questions? The other way that I think about it, again, and maybe this takes practice to kind of see it. You know, what you're trying to do is to translate one problem into another so your Bobilli solver does the right thing. And it's about trying to make penalties. You design your translation so Bobilli will be punished for picking the wrong solution, the one that doesn't give you the property that you want. Okay? And maybe you need to see more reductions to kind of get a feeling for this. But the kind of reasoning I'm going to be saying, well, if Bobilli picks this, then you're going to also have to pick this giant thing, and that's going to be no way that's going to do what you want. Okay? Maybe that's not clear, but maybe with some practice. And when I think about my transformation, there's kind of trying to do what I will say strategic decisions, which are at a high level. What are the general similarities between the two problems? And then there are tactics. How do I do the translation to make those similarities kind of come out? Okay? How do I force that either A is chosen or B is chosen, but both aren't? That in the optimal solution, that I have to pick either A or B. Remember when we did the vertex cover proof, I added an edge between V1 and V2, V1 and not V1. And I said, your bound of how many vertices you're going to pick is so small, you're only going to get to pick one of these or one of those, either this one or that one. So you'd better do it right. That's the kind of thinking I'm asking to do here. Any questions about that? If I am trying to prove that a problem is hard, at least in the real world, okay, sometimes I get stuck. And one reason I might get stuck is that I'm too dumb and I can't find an NP completeness proof for it. But the other thing is maybe the problem isn't hard in the first place. Maybe there is a fast algorithm. Maybe if I use dynamic programming or some powerful graph algorithm, there might be a way of doing it. Okay? So in real life, I kind of, if I try to prove something hard for a while, I can't do it, I start looking for an algorithm. If I'm looking for an algorithm and I can't find an algorithm, maybe I will try to prove it hard. Okay? And, in general, thinking about it both ways. Okay? Usually one will lead to an insight on the other. Any questions? Any question about my strategies? Okay, so what I would like to now do is my NP completeness challenge, okay? Where I'm going to try to figure out an NP completeness proof before your eyes, okay? And there's a book I have that's a wonderful book. It's an old book, but there's a book called Computers and Intractability by two guys, Gary and Johnson. And when they wrote this book, maybe I can even show it to you because we're on Zoom here. On what they did was show us is basically keep track of they had a catalog of all problems that were known to be NP complete at the time they wrote the book. Quadratic programming, hard. 3-set, hard. Non-erasing stack automata acceptance, hard. Okay. Permutation generation, hard. Okay. So this is a great catalog of hard problems. What I'm now going to do is encourage you guys to pick one. So does somebody have can somebody type this thing into this URL into their search engine, into their computer, their web browser? Someone tell me when you got the list of problems coming up. Has anybody got the list of problems?
I got it.
Yeah.
Okay. Two of you guys have it. Which one of you, let's see, do I want to pick one or the other? Just to show I'm not faking this. At the count of 3, one of you guys yell. First one to yell gets it. Somebody yell.
Ah,
Okay,
ND3.
good. You pick a number, pick a problem from that list.
all right. Let's try ND27.
What was it? ND.
Yes, network design 27.
ND was for network design. 27, is that what it said? ND 27?
Yep.
Okay, that's an interesting one. That's one I've never actually seen this one before, actually. I don't
Oh,
think.
excellent.
ND 27. Does everybody see this one? Okay, let's see if I've got that one. Is this really the number that I had? Is that the one that says rural postman? Do people see this? Am I holding this up in a way people can tell?
I see the postman. Yep.
So try to read that now for a second. I'll read it to you in a second. But what is this problem? This one says rural postman. I am given a graph. I am given a length. Okay, this is kind of a length for each edge, it looks like. I'm given a subset of edges. And I am asked, is there a circuit, okay, in G that includes each edge, okay, and has total length at most B? Okay. That's kind of an interesting question now. So let's just think about what that problem means, okay, if we talk about rural postman. So, where do I have my pen here? Okay, good. What is rural postman? Looks like the answer today. Rural postman. It looks like I am given a weighted graph, G, and I am given a bound, K. Wait, no, what am I given? A rural graph, and I'm given a weight bound B. Hold hold on, sorry. A bound B, and I'm given a collection of edges I have to walk on, right? And the question is, I'm given a collection of edges I have to walk on, okay? So I live in a world where I've got a graph like this. Let me say I'm making a graph. I am telling you I have to walk on this edge, and I have to walk on this edge. Can you find the shortest path, the shortest closed path, or a closed path where I'm allowed to visit, where the total length of my path is B? Okay, is at most B. Okay, let me think a little bit more about this problem now. I haven't quite explained it. What if I want to, given a graph, let's say I'm given a graph, let's look at one that isn't a close variant to something like this that isn't hard. What if, I'm gonna do what? What if I want to visit every edge in the graph? What if I tell you I want the shortest store that visits every edge in the graph? Does anybody know an algorithm for solving that kind of thing?
Hamiltonian Cycle.
Hamiltonian cycle visits every vertex in the graph, right?
Eulerian cycle.
Eulerian Cycle.
Eulerian cycle. So we got some alumni of AMS 301, I think, in the house, right? So Eulerian cycle says visit all the edges in the graph as cheaply as possible, meaning you're visiting them only once, right? Is the problem Eulerian cycle hard? Or is there a fast algorithm to tell if a graph has an Eulerian cycle?
That
Alumni
is,
of, what was that?
it's hard, yeah.
Hard to find an Eulerian cycle? A cycle that visits all the edges? Exactly
Well,
once?
Below a certain bound. It's hard.
Well, certainly if I have to visit all the edges, the cheapest way to do it would be if I visited every edge once, right? Now, isn't that problem, is that problem hard to tell me whether or not there's a way to visit every edge exactly once? Or did they teach that in AMS 301? How do you know if a graph has a way to visit every edge exactly once? Does anyone
I think
remember?
it has to do with the degrees of the
Has something to
vertices.
do with the degrees, right? The degrees of the graph had to be even, right? On this vertex, notice that every edge vertex has a even degree, right? Does everybody agree with that? And is there a way, according to Euler, if the graph has every vertex has even degree, there is a way to visit every vertex, every edge exactly once, right? Remember this if you took AMS 301? Remember you could go ka-chunk, 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 ka-chunk. Oh, no. Let me see. Okay, let me try a different color because I'm terrified by this. Hold on. Ka-chunk, 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 ka-chunk. Does everybody see that? So finding a tour, remember rule Postman is a problem about a circuit, meaning I'm visiting the edges, not the vertices, okay? If I want to know, is there a tour that visits all the cheapest tour that visits all the edges in a graph? This is the Eulerian circuit problem. And this, it turns out, is easy. It's just telling whether every vertex has degree to an even degree or not, right? So finding if I ask, what is the cheapest way? Is there a way, let's say whether the graph is unweighted. I'm going to make it even simpler. Let's say that the graph is of weight, all the edges were weight 1. Does everybody see that if I asked, given a graph G, if I said that the weight of the graph is the bound B is going to be the number of edges in the graph. If all the edges weight 1, and I believe in this problem here, okay, again, the other input just to check is that I am given some E prime here, a set of edges. The other thing that I need is a set of edges that I must visit. E prime is equal to the edges that must be visited. Okay? So if I said that E prime is equal to all the edges in the graph, this over here is just Eulerian cycle. And this would be easy. Okay? I haven't proven anything yet about hardness. I'm just trying to understand the problem still. I'm still grokking this problem, right? Do you guys, but I now understand the problem, I think. Do you guys understand what the problem is? I am saying I am giving you a collection of edges, okay, that you have to visit. I am wanting to find the cheapest tour that visits all these edges, okay, that I'm requiring you to visit. Why is this called the rural postman circuit? Let's imagine that somebody is living in some rural, godforsaken part of Long Island. Okay, you're a postman, and there's all these roads, and you have to deliver the mail to people. But in fact, in this part of most of these roads are not, they're not houses on them. Suppose I know that these are the only streets that have houses on them. If I'm going to be the, if I'm going to be the postman, I would like to find what is the shortest tour I can have to visit all the roads that have houses on it, right? That's what the rural postman is asking for, okay? Do people grok this problem now, or any questions about the problem? I sort of understand it, and I want to make sure you guys understand it, what we're asking for now. I am giving a graph, which is the blue thing. I'm giving the edges I have to visit, which are the red ones, and I want to find the cheapest circuit that will visit all of the red edges. Any questions about that? Okay. Any idea? Any questions about what the problem is? Okay. Now let's prove it hard. Any questions about the problem? I want to make sure people get it. Okay. So now how do we do it? Okay. What is my Bandersnatch? And what is my Bobilly? Does anyone want to tell me? Rural postman, is it going to be Bandersnatch or Bobilly if we're trying to prove it hard?
Bobilly.
Bobilly. So I've got rural postman here. And the arguments to it seem to be a graph, my graph G, my important edges E prime, and my bound B. right? So I know what my proof's going to look like schematically. What is my Bandersnatch? Anybody here want to propose some Bandersnatch that smells like rural Postman?
Would you use like finding the cheapest Eulerian cycle as your Bandersnatch?
Well, finding the cheapest Eulerian cycle, why do you know that's hard? No one ever told me that was hard. I don't know what that means. Okay. What problem smells like this? Okay. I see it on the thing, but what problem smells most like this to somebody? At least to I think Hamiltonian cycle to me smells like something. Hamiltonian cycle involved visiting all the vertices of a graph, right? That's what the Hamiltonian cycle was, okay? And how does Hamiltonian cycle smell like rural Postman? Ah, yuck. Hamiltonian cycle took a graph, we're going to call it G. Let's say to avoid confusion, let me call it H. That's what I'm going to do to avoid confusion. H. And I want to know, is there a tour that visits every vertex of H exactly once? Does everybody agree? Why does Hamiltonian cycle and rural Postman smell like they're the same problem? Does anybody have a sense of smell like that? In what ways are they similar?
They're both ordering problems.
They're both ordering problems. They're both saying, give me an order to walk around things in the graph, right? One was about finding an order of the vertices. One was about finding an order of the edges, right? So that's, I think, a way that they smell the same, right? Can anybody think? Okay, now it's my job to solve it. But does everybody now see that I need to do? You know what my strategy is. Okay. I want to try to specify a set of edges that I have to find the shortest tour between. Sort of cycle visiting all of them, right? Okay. I'll tell you how I think I'm going to do it. And we'll see if I can get away there. Any questions, first of all? My idea is the following. H is going to be a graph where you're looking for a Hamiltonian cycle in it, right? Let's say that this is my graph. Does everybody agree that that has a Hamiltonian cycle? I now need to find a way to translate this into a graph and a set of edges such that a weighted graph and the set of edges such that the cheapest thing is going to be it. How am I going to do it? What if I create as my gadget? These are going to be the edges that I'm going to demand to visit. What is that going to be? These are the edges I have to visit. Does everybody agree? Now, what if I think I may need this, I may not be. Let me surround this, each edge. Sorry. I think I made these blue on the other graph, so maybe I'll make these blue. What if I surround these by, I'm going to say, edges of cost 0? I don't have to visit all the vertices, but let's say all of these green things cost 0. Right? So green is going to cost 0. Let me even say blue is going to cost 0. What if I now say I'm going to connect this thing like this? Oh, sorry, I didn't finish making my transform a little bit. Those are 0, 0. What if I add these edges here? I hope I am going to keep this color the same, yeah. What if I make the cost of the blue, these edges, 1? Does everybody see what I'm now trying to try to do? I am going to now ask, does there exist? My claim is, the question here, does there exist a circuit, meaning an edge tour? That's what I'm going to call it, an edge tour. Okay. Visiting all blue edges. I'm going to say all blue edges with cost B equals N. Okay. Does anybody see what I've just done here? The only way, what is a cheap way to visit all the vertices and get back to all the blue edges and get back to where you started from? Does everybody see that a cheap way to do it would be to go bunk, maybe from here, bunk, here, walk up to there, go bunk, bunk. Does everybody kind of see that? If I have this graph, if I ask, is there a tour of length, a cost N, purple edges cost 1, all other edges cost 0, right? If I ask, is there a way to visit the blue edges and get back to where you started from at a cost of N, the only way you could do that is by visiting every vertex in the graph, okay? Exactly once. And that is a Hamiltonian cycle tour. Do people see this? Is there anybody who sees what I've done? Or is this still seem like it's from Mars?
I see it.
Okay. Anybody else? Any questions about that? You see how I did this transformation? Hamiltonian cycle was a question about how do I visit all the vertices, okay, without visiting any edge twice. Rural Postman is how do I walk on the blue edges and get back home as cheaply as possible, okay? And the question is, and you can see that I'm kind of, if all I'm paying for are the purple edges, the way to minimize the cost is to make sure I don't walk on any, I walk on the absolute minimum number of purple edges that I need to create a cycle. Okay? And that's going to be N. Why did I add those green loopy things? This is because I'm a little nervous about, does it matter which side of the edge that the blue edge I walk into or not? And by having the ability to pay 0 for walking around those green edges, once I walk into one, I can get to any other place at a, I have to cross through that edge. But once I've done it, I can walk around the green and not pay anything to get out to the side that I want it to be. That's why I added the green things. Does everybody kind of see that? Any questions about this reduction? It should be clear. If you see it, that's good. If you don't see it, you may have some problem grokking what the problems are. But the important thing is, this is an easy reduction. This doesn't look hard. It should be clear that whatever's going on in Skinner's head, this was not rocket science, okay? He's basically just drawing the same graph as you have there with a little gadget at every vertex. And if you understood what was going on, you see why that gadget was the right thing. If you could solve the rural postman quickly, you could give this kind of an input and it would find the Hamiltonian solution. If this thing had a solution of cost n, this thing had a Hamiltonian cycle. But it is hard to find a Hamiltonian cycle. So there can't be a fast algorithm for this asking whether or not this kind of a graph has a, a rural postman tour of cost n. Any questions about it? Do people see it? Any questions?
I had a
Professor,
question.
could you go back to the previous slide really quick? Sorry.
Funk. Yeah.
So is that one on the bottom right, like that blue graph that you drew, like does that translate to the graph that you drew on the slide right after this?
Right. So this is supposed to be a rural postman problem. This blue thing, okay, yeah. So I may have had my colors wrong, but yes, this is a rural postman instance. This was a rural postman instance, right? Okay. And, I don't want to, because I'm running out of time, I don't want to specify what the actual things are, but it should be clear that B is going to be n, the number of vertices. The graph is going to be this thing with the gadgets. The edges are going to be the edges, basically corresponding to each vertex of the original graph. I have to get my notation right to explain it by this. But I think if you look at this figure, you should be able to see clearly what I'm doing. Any questions about that? Okay.
I did have one question. Not necessarily about the way that you did it, but I don't exactly know how this would go down if you tried to do a reduction, but I was thinking, could you have possibly used an edge graph? Like if you could convert the rural postman graph to an edge graph where the vertices represent
notice
the edges.
I don't want to convert the rural postman graph to anything. I want to convert the input Hamiltonian cycle problem, my Bandersnatch input, to something. That's what my strategy is, okay? And if you pick a different Bandersnatch, the conversion is going to be different, okay? But this is a way to do it that it's nice, neat, and clean. Any questions about it? So I feel good about myself today. I think this is a pretty clear reduction, okay? And it shows me that the reason the rural postman is hard, it's hard when you have, a set of edges that, that play the role of vertices in Hamiltonian cycle. Any questions about that?
On the previous slide, should G be equal to H?
Should G be equal to H? The answer is no. This is H, this is G. Right? This is the corresponding G for this H. Okay? That's the idea here, right? I took my H and I constructed my G and I built my E prime where the blue edge is here and my bound was N. Okay? This was of weight 1. Now, if I added weights, that was, of course, 1, 1, 1, 1, 1, and every, no. Actually, the weight with that were all 0, excuse me. But the edges of the purple graph, the weights were 1, 1, 1, 1, 1, 1. Okay, that was my transformation. Any questions? Okay. If you got it, that's good. If not, take a look at it. Okay, it's not a hard reduction. I'm not going to ask that on the final, but I do think that that's actually not so impossible to understand. Okay, let me just end with a description about this whole idea of what the difference I use. Sometimes, where does the NP in P come, and NP come up in NP completeness? Okay, here we get into some sort of formal language theory, but some stuff you should know as a computer scientist. We say that a problem is in the family of problems NP if you can check its answer in polynomial time. If I show you, say, is there a traveling salesman tour of cost 96 in this graph? If I write down a tour, you can check, yep, it's a traveling salesman tour, and yep, the weight cost was weight less than 196. A problem that you can check the answer quickly if I give you enough stuff is an NP. A problem you can solve in polynomial time without the input, without being told the answer, is in P. Okay? So, every problem is in P or an NP. Actually, any problem in P is also an NP. If I asked you, could you check that the shortest path distance from I to J in a graph is less than 56? Well, you know about Dijkstra's algorithm. That's fast. You could compute the shortest path. Shortest path is in P. Okay? So it's easy. You can find the solution. Certainly, you can check it. Okay? So certain problems are in P, like is there a path of length less than something between I and S and T? In certain problems are in NP, meaning you can check the answer quickly, even if you can't give the answer. Okay? Even if you can't find the answer. Given a tour, it's easy to convince you it's a tour, but finding the tour is hard. There are even harder problems. If I ask you in a graph, how many TSP tours are there? If you tell me 6,793,246, to check it, you've got to list all of these tours, and even just listing all the exponential number of tours couldn't be fast. Okay? But almost any problem we have discussed this semester is in P, in NP, because we could check it if we had that solution. Okay? A problem is NP complete if it is as hard as satisfiability and it is in NP. Okay, that you could check the answer quickly if I gave it to you. Okay, any questions about it? Now, almost any algorithmic problem that is interesting, people know whether there's a fast algorithm or it is hard. And there's only two famous exceptions that I know of. One is it hard to factor an integer? You know about like the RSA algorithm for cryptography and things like that. The RSA algorithm is secure because it's hard to factor integers, supposedly. Okay? No one has a fast algorithm for it. But if they did come up with a fast algorithm, the RSA people would be in big trouble. Okay? There's not really a proof that it's hard. It's just that no one's found one yet. And in fact, quantum computers seem to be able to factor integers. So at some point, the RSA people will be unhappy. That problem, graph isomorphism, I told you. is another problem that no one knows a fast algorithm for, but they haven't proven it NP complete. But almost any other problem that's interesting, people know either it's hard or it's not hard. Okay. Finding the shortest path between two nodes is polynomial. Finding the longest path between nodes is NP complete. Finding a small set of edges that covers all the vertices, that problem is polynomial. That's a hard problem to show it's polynomial. It's something called graph matching. But finding a small set of vertices to cover all the edges, that actually is hard. Sometimes changing the wording a little bit is the difference between hard and easy. And that's kind of one of the things that makes this area interesting. The question that people call the greatest question in theoretical computer science, and probably one of the most famous problems in all of mathematics these days, is P equal to NP? Is the set of problems that we can solve in polynomial time the same as the set of problems that we can check the answer in polynomial time? Now, SAT is a problem that is the hardest problem in NP. Okay? It's the mother of all hard problems. No one has ever really proven that there is not a fast algorithm for satisfiability. There's very good reason to believe there's no fast algorithm. But it hasn't been rock solidly proven it. If you prove that there's absolutely no fast algorithm for SAT, then you would prove that P is not equal to NP. Because then there would be certain problems you could solve quickly, but SAT there would be absolutely no chance. Right now, we know that SAT is the hardest problem in NP. And it's never been really proven that there isn't a way to do it fast. I don't believe there's a way to do it fast. Okay? But trying to decide that is the question of P equals NP, which is a famous question in, the famous question in theoretical computer scientists. Every algorithms person should know what the question is. Any questions about what P and NP mean, or any implications, or any of that kind of stuff? People think they know the difference between P and NP. NP complete means it's the hardest problem in NP. Okay. And I think that means harder than anything than problems in P. But it's certainly the hardest problem in NP. Okay. Any questions about that?
Did you say another way to state that is it is in NP and there's a reduction from SAT for NP complete?
NP complete means that if I have a problem that's NP complete, technically it means that it is as hard as SAT and it is also in NP.
Okay.
Sometimes you will say that a problem is NP hard. That means that it's as hard as SAT. But maybe it's even harder than NP. Remember, I said some problems are not in NP, right? This is not in NP. Okay? But that's the kind of vocabulary that I wanted to kind of avoid. But the question is okay, you should all be convinced SAT is as hard as it gets of problems in NP. The question really is SAT, is it clear that there absolutely can't be a problem, a fast algorithm for SAT? Okay, that hasn't been proven. You prove that, you're famous. I'm quite sure it's true, even though it hasn't been proven. That should be your operating assumption in life. Okay, but that is the question of P equals NP. Any questions about that? Any questions about NP completeness, what NP complete means? Philosophical questions, anything like that?
Yeah. What would be the motivation to think that just because a problem can be verified in polynomial time, that it could possibly be solved in polynomial time as well?
Well, until you prove it can't, it's a possibility, right? It's a question of, is it harder to come up with a proof or to check it? That's really what it comes down to. NP means that you can check the proof in polynomial time, right? P would mean that you could come up with a proof in polynomial time. Is that true? Again, I sleep quite comfortably thinking that P is not equal to NP. And I give up when I have a problem that's NP complete. Okay? But ultimately, there's still a question there of whether that's really absolutely positively true. Okay? But as a practical matter, NP completeness proof, no algorithm, no fast algorithm. That's the way I deal with it. Any questions?
I did have one follow-up question to that, if you don't mind.
What is-
If you were to prove that P equals NP, let's say somehow, then how would you, even if P does equal NP, practically speaking, would you be able to find an algorithm for it, even if it does exist?
One great way to prove that P equals NP is to give a fast algorithm for satisfiability. You give a fast algorithm for satisfiability, my God, P equals NP. Okay? You're saying, is there some other way to prove it without giving that? Well, that now gets into some flaky things that I don't want to think about. You really want to prove P equals NP? Show me the algorithm. Okay? And then I'll believe you. Okay? If not, give me an argument that shows that there really isn't any algorithm. That's the crux of the P equals NP question. Any questions? Okay. Now, I will leave you with one last thought just to confuse you. Don't be fooled by anyone who tries to prove P equals NP by saying N equals 1 or P equals 0. Everybody see that? Does everybody see that P equals NP if N equals 1 or P equals 0?
I like that.
Okay, if you like that, good. If you don't like it, don't worry about it. It's not going to be on the exam. Okay, this part won't be on the exam.
I had a sort of a clarifying question about just doing reductions. When we do a reduction, what exactly is it that we're reducing?
We are translating one problem to the other to show that they are the same, that the hardness or the easiness is preserved.
Okay, so can we use the term translate then instead of reduce?
You can use translate, but I don't understand it. I would need, for me to understand it, someone would have to translate to reduce.
Okay.
Okay, the word that people use is a reduction. Okay. Any question about that? Okay, anything else?
I have a quick question about the homework.
Yes.
Do you want us to submit the code for question 1 as like a separate text file or in the document?
Yeah, why not submit the code? If you wrote the code, submit it. You should feel good about it. Okay?
Thank you.
Fair enough. If not, take care, good luck, and I will see you guys at the final. Okay, take care. Bye-bye.